nanoHUB-U, online instruction.
Welcome back. This is Lecture 3 of Unit 1. In Lecture 2, we began to get familiar with the IV characteristics of transistors. So in Lecture 3, we're going to talk a little more quantitatively about what makes a good transistor. What do device designers look for in those IV characteristics? So these are called device metrics, and there are a few device parameters that we will talk about as well. So you remember we talked about hooking the transistor up in different ways so that we had a two-port device, a two-port circuit, an input and an output. This is a common source connection. The source is common between the input and the output. And then we're interested in understanding these current voltage characteristics, the current that flows from the drain to the source as a function of the voltages on those three terminals. And we have transfer characteristics and we have output characteristics depending on which voltage we fix and which voltage we step or sweep. So here are the output characteristics. So in this particular curve, we have fixed the gate voltage at a specific voltage VG1. We're sweeping the drain voltage from 0 to the power supply voltage VDD, possibly 1 volt or so these days. And we get an IV characteristic that looks like this. These are the output characteristics. If I put smaller voltages on the gate, I get smaller currents. If I put larger voltages on the gates, I get curves that have higher saturation currents. So I get a whole family of characteristics that way. If I just look at one of those, each of those has a linear region where we have a small voltage between the drain and the source, and a saturation region where the current is less sensitive to drain voltage and tries to saturate. That's for a high voltage. There is a specific drain to source voltage. You can see it's not precise, but it sort of separates the linear region from the saturation region. We call that the drain saturation voltage, VD-sat. Now, let's look at these IV characteristics. The slope of the IV characteristic in the linear regime, that is related to the resistance. 1 over the slope is the resistance of the transistor when it's operating in the linear region as a gate voltage controlled resistance. So we can just take the slope at that specific gate voltage, take 1 over the slope. We'll call that RDS. That's the voltage, that's the resistance that we would deduce between the drain and the source terminals at that specific gate voltage, VG1. All right, so if it is an experimental characteristic, it's easy to read that slope off and determine that value. In the output region, we also have a slope, and that represents the output resistance of that current source in the saturation region. So if we take 1 over that slope, at this particular input voltage VG1, we would get little R sub 0. We call that the output resistance of the transistor. So those are two important parameters. Now, if we look at those output characteristics, there are several things we should mention. We're assuming that we're above threshold. That is, the gate voltage is big enough that current is allowed, significant current is allowed to flow between the drain and the source. If the gate voltage is not big enough, then we would call that the subthreshold region. Small leakage currents would flow, and those small currents are important these days, but they're too small really to see on a linear scale like this. The linear region is for voltages that are less than VD-sat between the drain and the source. The saturation region is for voltages that are larger than VD-sat. The output resistance is the resistance in the saturation region, and this drain to source resistance is the resistance in the linear region. Normally, when we're quoting these values, the gate voltage we'll use to do that will be the biggest gate voltage available in the circuit, which is VDD, the power supply voltage, perhaps 1 volt these days. Okay. Now, I want to mention when we discuss some parameters in the next few slides that remember that the width of the transistor, the dimension coming out of the page when I draw these cross sections, that we call W. And the current just scales with W. If the transistor is twice as wide, twice as much current flows. So people usually quote the current in microamps per micrometer of width, or milliamps per millimeter, or amps per meter. You usually quote it in current per unit width because the designers will decide what width they want to use to get the current that they need. So we'll have to keep that in mind when we look at some of these units. So let's talk about the first set of device metrics that a designer would look at. So a key one is what device designers would call the on current. You apply the maximum voltage to the drain. You apply the maximum voltage to the gate. This is the maximum current that you're going to get out of the transistor in this circuit. We call that the on current. It's usually quoted in microamps per micrometer. Okay. Output resistance. Again, we're usually interested in the output resistance. We'll see a little bit later why that's important in circuits, but we're usually interested in it at the highest gate voltage possible. So we take 1 over the slope in the saturation region. Now notice the units, because this is the change in current. It's a change in drain voltage divided by the change in current, but we're measuring the current in microamps per micrometer. So it means that we'll quote this output resistance not in ohms, but in ohms-micrometers. So if my transistor is 1 micrometer wide, I'll have one value. If my transistor is 2 micrometers wide, I'll have half the output resistance because it's like resistors in parallel. So some of the units take a while to get used to. Now, transconductance is another really key figure of merit for a transistor. The transconductance is basically, if we change the gate voltage, if we increase it a little bit, what is the increase in the drain to source current? So it's delta drain to source current divided by the change in gate voltage that produced that delta. So the units are Siemens, but remember everything is being measured per micrometer, so we typically quote these numbers in microsiemens per micrometer. If you have a transistor that's twice as fat, you'll have twice as much transconductance. Okay, so those are some key parameters in the output characteristics. Let's look at the transfer characteristics. So remember, in the transfer characteristics, we fix the drain voltage and we sweep the gate voltage. So if we fix the drain voltage at some particular VDS, we'll get a curve that looks like that. If I look at that a little more carefully, if I fix it at a low drain voltage, now I'm operating in the linear region and I'm sweeping the gate voltage. And I'll get a characteristic that will look like that. If I fix it at a large drain voltage, now I'm operating in the saturation region. And for small gate voltages, the transistor is still off, but for large enough gate voltages, the transistor is on. The transition between off and on, it's not a precisely defined quantity. It's when significant current begins to flow. And we call that the threshold voltage of the transistor. So just looking a little more carefully at that, if I look at it, if I apply a large voltage to the gate, apply a large voltage to the drain in this particular curve and do that transfer characteristic, then when I get the gate voltage up to the power supply voltage, then I've got the maximum voltage on both the drain and the gate. That's my on current. If I apply a small voltage between the drain and the source, I get another transfer characteristic. Smaller voltage, I get less current. Now, if I'm interested in the threshold voltage, what I might do is to draw a straight line on this transfer characteristic and find its intercept with 0 current, and I'll call that the threshold voltage. But notice that if I do that with a smaller drain voltage, the intercept is different. So people frequently talk about 2 different threshold voltages. There's a threshold voltage for the device operating in the saturation region, and there's a threshold voltage for the device operating in the linear regime. Ideally, those 2 would be the same. The threshold voltage would not depend on the voltage we apply to the gate. But in practice, there is some small dependence. We'll talk about the physics of that later. So there is a drain voltage dependent threshold voltage. There is actually some current flowing below threshold, too small to see on this plot. The way to see it is to plot the current on a logarithmic scale instead of a linear scale, because this leakage current is important. These days we have billions and billions of transistors on a single chip of silicon. Even when they're off, a little bit of leakage current is flowing, and when you multiply that by the billions of transistors are there, this has become quite significant. So we need to look at that off current. So if I plot it on a log scale, this is what the transfer characteristic would look like. It's the same transfer characteristic we showed on the previous slide, just plotted on a log scale. Okay, now we can read off what we call the off current. So the off current is defined we have a large voltage between the drain and the source, but we have no voltage on the gate. The transistor is supposed to be off, but there is some leakage current flowing. We can just read it off of this log plot now. Now, I might define an arbitrary current. Some current here that I'll say when the current is bigger than this arbitrary current, the transistor is on. When it's less than that current, the transistor is off. So my threshold voltage is going to be, when I hit that arbitrarily defined current. Different people will define it in different ways. It's just another indication that VT is not a precise number. If you're comparing VTs with some other lab or some other group, you have to be sure that you understand how each of you is defining threshold voltage, because it might not be the same. Okay, now an important thing to understand is that below threshold, the current goes exponentially with gate voltage. Above threshold, it behaves much more slowly, and we'll talk about that a little bit later. Now, below threshold, there is an important device parameter that device designers worry a lot about, and that's something called the subthreshold swing. So if we look below threshold, where the current goes exponentially with gate voltage, straight line on a linear plot, then I can ask myself, how much change in gate voltage does it take to get a factor of 10 increase in the current? We call that the subthreshold swing, and we measure it or quote it in millivolts per decade. It means how many millivolts does the gate voltage have to increase in order for me to get a factor of 10 increase in the drain current. That's the subthreshold swing, and that's a really important device metric. Okay, we're going to define several of them here, and it's important for you to spend some time getting familiar with these, because we'll refer to these and talk about the physics of these metrics throughout the course. So let's look at this transfer characteristic. And let's say there's an arbitrary current we're looking at here. This is a transfer characteristic plotted with a large voltage between the drain and the source. So we're operating in the saturation region. Let's do the same transfer characteristic at a low voltage between the drain and the source. Typically, people would use 0.05 volts, sometimes a little bit different. So we get less current. But the interesting thing to notice is that we get a horizontal translation in the curve. So if this arbitrary current is the current that I'm defining threshold as, if you're bigger than that, you're on. If you're less than that, you're off. Then what this says is that the threshold voltage has changed. All right, we saw that earlier. There's a VT sat and a VT lin threshold voltages in the linear and saturation region. And we're just seeing the same thing here on this log plot. So the IV characteristics, if it's a good transistor, then these slopes don't change. We just translate the IV characteristic by an amount horizontally, and we call that drain-induced barrier lowering. Lots of terms to remember here. It's called drain-induced barrier lowering because that describes the physics of what causes this. And we'll discuss that later in the course. But this is measured in millivolts per volt. So it's how many millivolts of horizontal translation, or how many millivolts did the threshold voltage change per volt of change in the drain voltage, from VDD to this small voltage, maybe 0.05 volts. That's what we call DIBBLE, drain-induced barrier lowering. Okay, so lots of terms. Spend some time getting familiar with them. On current, off current, subthreshold swing, DIBBLE. Some device parameters like threshold voltage in both the linear and saturation region, the drain to source resistance, 1 over the slope in the linear region, the drain saturation voltage, which tells me the division between the linear region and the saturation region of the output characteristics, the output resistance, 1 over the slope of the IV characteristic in the saturation region, and the transconductance. So these are all very important device parameters and device metrics, and we're going to discuss the physics of them in the course. So here's an example that you can practice on. Here are some measured IV characteristics. See if you can deduce the device metrics from these IV characteristics. And you can do it in eyeball. So these are the output characteristics. My power supply looks like it's 1 volt. This top line here is a gate voltage of 1 volt. That point there, which looks like 1.55 milliamps of drain current per micrometer of width, that looks like the on current. If I want the off current, I look over here on the log plot. The off current is defined when I have the maximum voltage on the drain and I have 0 voltage on the gate. That looks like 10 to the minus 7th amps per micrometer. So you can go through these and just kind of eyeball them and see if you can get these answers that I got when I went through and just tried to roughly read these curves off. And if you can get these answers, then it means you have an adequate understanding of device metrics and device parameters. And then one more thing. Remember, most of the time, just in the interest of time and because the concepts are the same, I'm going to be talking about N-channel transistors. But CMOS technology has just as many P-channel transistors. All of the voltages change sign. All of the currents change direction. The IV characteristics flip around and look like this, but they're basically the same. It's just everything is flipped. See if you can derive the device metrics and device parameters, the same ones that we did for the N-channel parameters, do them for the P-channel transistors. And if you can do that, then you understand these device parameters well enough that we can continue with the course. So what we've learned in this lecture is how to extract some of these key parameters that we're going to be talking about throughout the course. Most of the course is going to be trying to understand what physics controls these parameters, both qualitatively and also quantitatively. How do we get a high on current? But in the next lecture, what I want to do before we dive into device physics is I want to talk just briefly. Device designers want a high on current. They want a low off current. Why? So we need to talk just a little bit about circuit design, basic CMOS circuit design, so we can appreciate why these device metrics are so important in determining the performance of the CPU that you carry around in your laptop or your smartphone or whatever. So the subject of the next lecture will be a brief look at how device metrics relate to circuit performance. So thank you for listening.